Last time we looked into Postgres extensions for document storage and analytics, and also showed how much more efficient specialized column stores can be for analytical queries. Today, for part 3 of the PostgreSQL Maximalism series, we will look into time series management using anomaly detection as a cool excuse to showcase timescale DB. And we'll also cover vectors and AI, taking a peek at recommender systems and RAG by using PGAI to compute text embeddings and the most similar movies to the user profile, while presenting a nice summary of that selection based on an LLM. Let's have some fun! So let's now look at the extensions for time series. Just for reference, like we did before, we include a few examples of database management systems outside of Postgres. We've got InfluxDB, which is known for its Flux language, and it has more recently implemented their own SQL dialect. There is Prometheus, which is well known for integrating with Grafana for monitoring systems, for example, and there is Amazon TimeStream just for as a cloud example. For extensions, we found two major ones, Timescale DB and PG time series. However, there is an interesting detail about PG time series. They were created by Tembo, and let me just switch into the browser here. So if we go into the website for Tembo, we can now see that they are focused on the automation of engineering tasks in relation to AI workflows. But previously, and they still have their legacy website, they were focused on providing a cloud for multi-workload Postgres. Their PG time series extension is open source. I'm not sure whether they are still going to maintain it or not. Probably they are, but their focus is moving away from this. Also, something I noticed is that the documentation for all of these extensions, so PG time series, it used to live on their website, as you can see, but you can seem to find it on the new website. They are probably migrating, I would say, but I'm not sure whether they are moving away or if they are migrating the documentation, or if they're just focused on their new target, new main business. But yeah, either way, we ended up going with Timescale DB just because they have a wider range of functions that provide many utilities to work with time series. Like filling in gaps, date gaps, or interpolation, or locf, which is the last observation carried forward, which just means that for missing values you will keep the previous value. And they have all the features of PG time series and more, except they have some limitations in regards to the license. And I believe this is why PG time series was created. Overall though, there is still a core package that you can use for free, so this shouldn't really be a problem. So let's now dive into the demo. And as usual, here in VS Code under the SQL directory, you'll find a directory for the category we are now looking into. So for time series, we're going to first load some data, and we are going to use the data from the previous example, YouTube data, and we're going to just create a hyper table for this data, which is the main structure for Timescale DB. So let's do this. One thing that is important is that you add the timestamp to your primary key, and let's go into the terminal and run pgcli. Let's now create our table. Okay, as you can see, you'll find a YouTube TS for time series table. Now next we will need to determine the temporal chunk size. This is for partitioning the table. Although we don't have large data, we're going to do it anyways just for demoing what this would look like. So first we look at the 6 most recent months. So we're going to do this based on the most recent months, just because we are assuming that the data might be huge, and this would take just too long if it's not done based on a sample. We don't use a random sample because the most recent data should be more indicative of what kind of dimension you will have. So let's just look at each stage of this query separately. So first, one thing we are going to do is select the month, the most recent 6 months from our data. Then we are selecting a sample from based on these dates from or not a sample but a subset based on the most recent months from our YouTube data. And then we're going to compute the range of the number of records that we have for a given time period. For instance, per day, per week, and per month. So this will tell us the mean n will be the lowest number of records that we have in a month, and the maximum number of records we have in a month. And then we'll use PG column size to compute the size in megabytes and just average that size so that we know on average how much space this type of partitioning, for instance monthly, will take if we decide to go with a partition per month. And so let's copy this over into pgcli. And as you can see, we don't have too much data, so it's sub megabytes for a day's worth of data. It's about 2.5 megabytes for a week's worth of data, and it's only 10 megabytes for a month's worth of data. And so we are simply going to partition by month, although this doesn't require partitioning with such small data, but we are just trying to generalize to big data or large scale use cases. And so getting back to VS Code, we can now adjust the table types for performance, or else timescale might output some warnings. For instance, in this case it will output a warning, and I believe it will also output a warning for when you are not using a timestamp with the UTC time zone or without time zone. So let's do this. And now let's create the hypertable, which is just done by calling this create hypertable function. You give it the table name for the table you want to transform into a hypertable, and then you give it the interval for partitioning. In this case we are using a month. This means we are expected to get partitions of 10 megabytes, which is nothing really. And then we also migrate data because this table already contains some data. And let's run this. Okay, and now after 6 seconds we do have a hyper table. So our hyper table is still YouTube TS, and we'll do our operations as usual over this table, but it is now partitioned and it is now optimized for working with timescale DB. So now let's go into a demo about policies. So one thing that is essential when you are getting real-time data in high volumes is to have some kind of compression. In this case, for us to enable compression in a hyper table, we need to set timescale DB compress to true, and then we need to add a compression policy. For instance, this compression policy, which uses an interval of 1 month, means that any partitions whose most recent date is 1 month ago, they will get compressed. So let's now set the compression policy for this YouTube table. There we go, there was no compression policy set, and now we have a compression policy. Now we can also set a retention policy. If you've got too much data and you don't need your older data, you've already analyzed it, got your analytics and your lakehouse full of summarized statistics about your data, and you can now delete it. Then we can set a retention policy, and like a compression policy, it will take an interval and it will remove the data that is older than, for instance, we are using 10 years here, so if it's older than 10 years from today's date, it will be deleted. So before doing this, let's look at our time temporal coverage or time range for our data. Now our data is from 2019 to 2020. This means that we should keep at least, given it is 2025 now, we should at least keep 6 years of data. So let's just use the 10-year policy. Again, let's do this. And there we go. The way this works is a job is set to be run and to delete all the records, and you'll be able to look at this job by running this query and to make sure that it's been scheduled and even started. As you can see, there is one entry here. There is already a last run that succeeded, and the next run will be tomorrow. Okay, and let's go back here and let's make sure any data wasn't erased. It shouldn't be, because we are using a 10-year period for this. As we can see, all our 1.5 million records are still here. Now let's try to change the policy to delete at least 6 months of data. We are just picking the difference between the current date and the maximum timestamp and 6 months ago, and so we can add a new retention policy that will show us how this works. We have added the new retention policy. We can check the jobs to see if there is a new job ID, and we can find this 1002 job ID, which is the new retention policy. And now we can also make sure that the job is run by doing something like this. So we can call run job with a job ID, and we can find what that job ID is by querying the timescale DB information jobs table, and the proc name will be policy retention, and the hyper table name will be our hyper table. And let's say that we want to make sure it's been deleted, so let's copy this over, let's paste it here. If we go into the jobs, we'll see that a job was just run again, for this task. Now we should look into the data, and half of the data will be deleted, and this is what happened. We no longer have 1.5 million but 766k records. Now let's just remove this retention policy, reinsert the data that we deleted. So we are going to insert everything again, and on conflict do nothing so it doesn't insert the same records twice. And then we are going to look and count to make sure our 1.5 million records are back. So let's first make sure we remove the retention policy. And there we go. Let's now insert the missing data. This needs to be done on separate transactions, I believe. Otherwise this insert will not work as expected. And finally, let's just count to make sure we have the 1.5 million records back, and we do. And so now we can move on into the next topic, which is features. And now for features we are going to look into timescale-DB's features. We're not talking about machine learning features here. And first let's look at the temporal coverage for datasets again. And so we have data from the 15th of April 2019 to the 14th of April 2020. And now one thing we can do is to use this time bucket gap fill. You will have to group by these buckets. We also order by it just for readability, and this means that we'll aggregate our data by day using the timestamp column, and we are going to compute the average views for each day, and we are going to look at this time range, which is the full range for our data, and whichever days do not contain any data, they will still be filled in, but we'll have a null value since there are no views to compute over here. Let's test this out. And as you can see, most of the days are filled in, but a few have no data, and that has been filled in by the time bucket gap fill function, although it has no value. Okay, so let's go back into VS Code. In here we have an example on how to fill the gaps using two different methods. So these two methods are either interpolate or lockf, last observation carried forward. This will just copy the value while it's null, it will fill in the same value that it has last seen, and interpolate will try to compute the natural progression between the previous value that was filled in and the next one. So when we are calling interpolate, we give it the field we want to use for interpolation. We can also optionally give it the value for the default if there is no previous value, or the default if there is no next value. And then let's just copy this into pgqi. Okay, let's run it. Again, we are returning the original average views, and then we are returning an interpolation and the carried value. So let's go down and look for the nulls on the first numerical column. For the interpolation, as you can see, it will try to fill it in with values that try to represent the natural progression from 1.4 million to 2 million. And over here it will just carry this 1.4 million up to the 20 million. It really depends on your application, but this is available just as a function, which is much easier than having to implement this in pure SQL. Another interesting feature from timescale DB is continuous aggregates, which is a kind of incremental materialized view. An incremental materialized view is a materialized view that gets updated based only on changed data. So in order for us to create this kind of continuous aggregate, we can treat it as a regular materialized view. Let's make sure that there is no previous leftover materialized view from previous tests. Okay, and now let's create this materialized view, which is created with timescale DB continuous. This is the difference between a regular materialized view and the continuous aggregates. And then the select for this query cannot have CTEs, so you cannot have subqueries over here. And we are creating this weekly stats, so we are using time buckets of 1 week. We are not filling any missing values. We are using the last value per week based on the YouTube video. So for each week we are going to take the last value for each YouTube video, and this will be the views, the comments, the likes, dislikes, and the likes share, the dislikes share. Okay, let's copy this over and try to create it. And there we go, we now have a continuous aggregate that will get updated as new data comes in without having to rebuild the whole materialized view from scratch. We can select from this materialized view to check out the output. We'll get something like this. We have the stats per week for each of the 11k videos. Okay, and now we can call refresh continuous aggregate whenever we want, manually, or it will be done automatically as well. We can force it if we need to, so by calling this, we give it a start and end date, and we give it the name of the continuous aggregate. You can add this continuous aggregate policy for automation, and this will essentially works like your compression or retention policies. Just creates a job for it, which calls the same refresh continuous aggregate, and we just created the jobs. And so we should again see these two jobs if we filter. It's done in a similar way as before, and as you can see there are two jobs for materialized tables, because we have two materialized tables as well with a refresh policy. And now we can also add compression policies for these tables. It works in the same way as the regular hyper table. Let's just do that. There we go. Finally, let's look into hyper functions. We are going to downsample or smooth the number of comments, and we are going to look at the companion notebook for the plots, so we can see what the effect of applying these functions really is. So we are going to create a function so that we can reuse it. This function will return a query where we just group by week we get the total number of comments. Then we create a time bucket per week and select from unnest based on LTTV, which is one of the downsampling methods they provide. You give it the bucket, the column for which you are downsampling, and then the sample size. In this case we are sampling down into just 10% of the original size. And in here we also we do it with a different downscaling function, which is ASAP smooth. It works in a similar way. And finally we just sum the number of comments per week, and we are going to look at that. So let's just create the function. And let's now look at the output of the function. And here we go. We've got the original comments, and then we have two downsampled versions, two smoothed versions. And now let's look at how this affected the data by looking at the visualization of this data. Let's go into the Jupyter notebook, so we can just run Jupyter Lab. So again, let's run the setup, load our environment variables, set up our Postgres connection variables, and now let's jump into the timescale.db toolkit, and we can now query from our function and look at the output data over here. It's the same data we just saw in the terminal. And then we have the LTTV, which is the largest triangle 3 buckets, which is the first column. And then we have the ASAP automatic smoothing for attention prioritization, which is a method for smoothing on this column. As we can see, the downsampling method, LTTV, is able to capture the trend but not the magnitude. It's much lower than the original data, while the ASAP is just a smoothing method that is a lot closer to the original data, although it seems to be lagging. I don't know exactly why, but it's probably just because it's doing some aggregations internally or something. So if I were to use one of these methods to just capture the trend, I could very well use LTTV, but if I want to capture the magnitude as well and have a sample of data that is close to the original data, then I would probably use ASAP. And let's go back to VS Code again. Finally, there is a histogram function, which can be quite useful as well. So in this case we are computing this histogram for likes to see how they are distributed. So you just give it the column you want to create the histogram for as the first parameter. You give it the value of the first interval. You give it the value of the last interval, and you give it the approximate number of bins. This should actually be 1 million. Give it the approximate number of bins. Let's copy this over to the terminal and look at the output. And here we go. We have 52 values with the number of likes between each range. So next we are going to jump into the recommender system, and before we do that, let's look into the blog post I got inspiration from to implement this. And so this is a post by booking.com where they just provide a very naive way to implement anomaly detection. Then they build on top of it, and it's actually something quite well thought of, that is not too complex to implement. So what they do is essentially based on a standard deviation. They compute, for instance, the weekly average for the time series, and they take several weeks and exclude the weeks that are anomalous themselves, recompute for the weeks that are considered normal the average, and then they can use the standard deviation and in conjunction with the z-score to determine whether the current week contains anomalies. So it's this would be an anomaly like they are showing here. This is the standard deviation. This also means that your data should follow a normal distribution for this to be viable, and we'll get into it next, because this was an issue for our data. Then you have the two bands for +1 standard deviation, -1. We usually use 2.5 to 3 standard deviations away from the mean, so a bit more than this, and this is more or less what they use as well. And then they rely on the z-score, which is not just a normalized way to output the number of standard deviations from the mean. And then they have a bunch of details over here on anomalous scores from the previous week that we need to exclude. So problems with z-score based alerting. I've implemented most of this in SQL. I'm not sure if I implemented all cases, but I implemented enough to make it viable and to demonstrate this. So let's now go back into SQL. Let's start by looking at the data and making sure whether it is normal or not. So I created a function to test normality over here. Since we had the Python module installed, we can actually create a Python function as long as our system's Python has the libraries that we need. So I needed NumPy and I needed SciPy for this. There is a normality test over there that we can use. So let's just make sure this function is created. Now let's also create a function to test a power law. This is a more intensive computation. You can use the power law library for this. So the way this works is on our Docker image, just out of curiosity, if you go into our Docker file, you will find some extra Python packages that are built with PGAI, which is an extension I'll cover next, but it requires the PL Python extension. So I took that opportunity to also add some extra Python packages, and this is where I installed them system-wide. So let's create this test power law function. Okay. And then let's test for normality, log normality, which we can just use the normality test with a log transformation. And let's also test for power law. So let's do one by one. Notice that we are also using a sample of only 1,000 elements, just because if there is too much data, this would take forever, particularly for the power law one. So let's look at the one for normality. As you can see, none of the data seems to be normal. We are testing this per week. As you can see over here, we are doing it on weekly stats. So it's not normal, which is a problem for us because we cannot implement the method based on z-score and standard deviations. If it's not normal, it will likely not work. So let's test for log normality as well. Is it log normal? It's also not log normal. And is it a power law? Since we are using a sample. So it's also not a power law. It probably is close to one of these, but not formally either of these distributions. So what we end up doing is we create a function to convert any distribution to a normal distribution. There are two methods that we can use, and in particularly we are using the power transformer over here. So let's create this function. There we go. And now let's convert this into normally distributed data. But before we do that, let's change this max tuples decompressed for the ML transaction to 0. So it's essentially disabling this because due to compression and since we are doing this over the complete data set, we were hitting some limitations with timescale for our data. So we do it like this and also set it to 0 for this session. And now let's create a non-C materialized view. This materialized view will contain our normally distributed data that we are going to transform here. And there we go. Let's look at the data that we created. And here we have it. It's normalized with a mean of 0 per week, since we are trying to compute anomalies over the weeks. And now let's test for normality, this time based on the view. And most of the weeks are now following a normal distribution. For those that aren't, what I did was I did a visual analysis because they might still approximate a normal distribution. They are just not formally a normal distribution, either to having too little data, a low variation, or there are just some outliers that and those are the anomalies that we want to capture, so they really don't follow the normal distribution. So let's look at the visualization to make sure that our transformations had an impact. So let's go back into our notebook and let's go into the dislikes distribution, which is what we were normalizing previously. Let's select the normalized dislikes and compare it with the original value. This is what we have here. And now let's look at the distribution for the original value. As you can see, we are in log y, so this is a really skewed distribution. So we can look at the percentiles over here. This will give us additional information. And let's improve readability by excluding the 95% percentile. We're going to visualize 339 records versus the original 357. And now let's look at the transformed values. And as expected, we do have a somewhat normal distribution over here. So we should be fine to now use this normalized number of dislikes to find any anomalous dislikes within a given week based on previous weeks. Now let's go back into VS Code and let's go into the anomaly detection task. And so we're going to pick a week for testing that might be anomalous. I looked at the data, and this week for December of 2019 looked like it was somewhat anomalous. Let's just look into it and confirm it is as expected. So this is our data. We are going to look at the December week. As you can see, most number of dislikes, and this is, we are looking at average dislikes. Average dislikes are mostly around 2 to 3k up to this week, so this 20k would be anomalous when compared to previous weeks. So this is a good week to test our anomaly detection system. Okay, so let's skip this week. This is the article I was showing you just before, and from the article I compiled a number of steps that should be done in order for us to implement this in Postgres. First, we need to compute the mean and standard deviation for each existing week, so we need to compute 4 z-scores, so based on this data. For the previous 4 weeks, we are using 4 weeks. The previous month will dictate the normality for the current week. And we are then normalizing. This is a technique that was used in this article. We are normalizing absolute z-scores, so we are not looking at positive or negative z-scores. It doesn't really matter. It just matters whether it's a large deviation from the mean. We are going to look at absolute z-scores, but we are going also to normalize it and then exclude the weeks with a normalized z-score outside of a 0.6 range of the median normalized z-score. This means that if one of the weeks is too different from the other weeks, then it's probably an anomalous week and it shouldn't be used as reference for normality. And then we compute a single absolute z-score based on a mean and standard deviation of those selected weeks. So again, we aggregate and compute the mean and standard deviation for those selected weeks. Let's say that we removed 1 week and kept 3 weeks. We'll take all that data and compute the mean and standard deviation, and then we will signal an anomaly when the absolute z-score is larger than 2.5. so we need to compute the z-scores for each value on the week that we are testing, and then any z-score that is larger than 2.5 will be considered an anomalous entry. Let's first run step 0, which is computing the mean and standard deviation per week. We are going to do this based on the previously computed views. So let's create this materialized view where we have the average, which is a function from timescale, and let's do it. And we have the materialized view. Let's just look at it. YouTube TS stats. And we have the average dislikes, the standard deviation for dislikes, and we have the same for the normalized dislikes, which is the one that we are going to use. So now for step 1, we are going to compute the absolute z-scores. We're going to do this based on a temporary table. It should exist for this session only. Let's create this table. There we go. And now we are going to look at actually the 6 previous weeks, not the 4 previous weeks, and we can check it out by running this subquery to make sure that's what we are doing. There we go, we have six previous weeks. And now we are going, based on these 6 previous weeks, we are going to insert a bunch of records into this week's selection table, where we are going to compute the absolute z-score for the dislikes, which is just the number of normalized dislikes minus the average dividing by the standard deviation. We're just going to copy this, and we have our temporary table ready. Let's just look at the temporary table. This is what we have for each video. We have 6 entries. We are only looking at this particular week, and then we have the previous z-scores for the previous weeks. And now let's go into step 2, where we're going to compute the median normalized absolute z-scores, so we can select which weeks to keep. And now let's compute the median z-scores, and we're going to delete the weeks from this temporary table where the normalized z-score is above 0.6. So what we are doing here is we are computing the median of the absolute z-score, which was computed previously for the temporary table. Then we are normalizing this by subtracting the median and computing the absolute value. Then we are deleting whatever is outside of this 0.6 range. Okay, we actually deleted no weeks, which is fine. It should be probably the most normal case. Now let's go into steps 3, where you compute the stats for the selected weeks, the absolute z-score, and then decide whether each record is or isn't an anomaly. So let's create a table for anomalies for this particular week. This table will be created based on the week stats for the selected weeks, the average and standard deviation. We then, based on these week stats, we compute the z-scores. If for some reason standard deviation is 0, then we just return 0. It's fine. So let's copy this. And now we have a table that contains all of our anomalies. Let's look at that table. And now, for instance, we've got for this video, in this particular week, we have an anomalous value of dislikes. We could go and look into this video. Let's see if we have any other. There is another one here, and this is quite deviant. You can also inspect our YouTube anomalies and give it a few conditions, so we can select just the anomalies and the ones with most likes, for instance. So the one with most likes we are ordering by likes in descending order and limiting to 1. We can also look at the one with most dislikes and the one with most comments and least comments. So let's look at these stats really quickly. So let's randomly look at one of these videos, for instance this one, which has the least comments. which is kind of interesting that it is a trending video with so little comments. Let's just check out what we are looking at. Okay, and this is apparently a video that is not available, and it is an NBC Sports video. Okay, it's just not available in my country. It's probably just available in Korea or something like that. And that's it for exploring basic anomaly detection using pure SQL. And let's now go into vectors and AI. As usual, we have a few references that are on Postgres. We got Pinecone, which is the original vector database, perhaps the first one that really got traction. And then we have Weaviate, Milvus, and Azure AI Search. All of these are mostly focused on generative AI and particularly semantic search and RAG. For Postgres, we are going to use PGAI, and PGAI depends on both pgvector and pgvectorscale, which are two solutions for indexing vectors for k-nearest neighbors computation. pgvectorscale is just an extension of pgvector, which adds a different type of approximate indexing, which is inspired by Microsoft's disk ANN. We also considered pgrag, which is still experimental and it's quite new, although it already has some interesting features like support for re-ranking models, which improves the outcome for RAG by re-ranking the retrieved results. And then we also considered pgvectorized by Tembo, which is quite similar to PGAI, but we just went with PGAI because it supported both pgvector and pgvectorscale, and pgvectorized does not support pgvectorscale. Also, in our previous time series solutions, we went with timescale, so PGAI would integrate better with timescale. So let's get into a bit of an example on VS Code. Again, you can find the proper code under the AI category for this one. Although this is based on timescale, still it's from the same company. We are going to disable timescale temporarily because we are going to use our lakehouse, which is based on PG Mooncake, to load some data about movies. So, like we did for the YouTube data, we're going to create a column store on our lakehouse schema, and we're going to insert into that column store a Hugging Face data set for movies. Okay, and let's do that. And we are done. It took almost 40 seconds to load. Now let's go into VS Code again and let's look at first 100 records just to get to know the data. It just failed because on this session we still have timescaledb loaded. So let's just quit the session and restart it again. And now we should be able to look at the records. So we have a bunch of movies, an ID, a title, the genres, which are just strings separated by a dash for each genre. We have the original language, we have a text overview, the summary about that movie. We have the popularity, the production companies, the release date, the budget, the revenue, the runtime, I believe in minutes, the status, whether it's been released or it's in the future, a tagline when it exists, the vote average and vote count, so we can know whether this rating is trustworthy. So if there are too few vote counts, it probably isn't trustworthy or representative. We got the credits, which includes everybody that worked on the movie. We've got a few keywords as well, and then we have some metadata that we are not going to use here. Now let's look at the temporal coverage of this data set, the min and max date before now, because it also includes some movies that are not released yet. We are not going to consider that. And so we have a movie from 1874 apparently called Passage of Venus, up to Aladdin 2, which is from May 2025. Now let's look at the embeddings. So first we are going to create a table of movie features, because we want to demo how we could use text, so based on text embeddings, vectors that represent that text semantically, and combine that with other features. So we ended up not going with the movie features, but I'm going to show it to you how to compute those features anyway. So essentially what we do here is we standardize, normalize a bunch of features like popularity, release date based on the year, the budget, the revenue, the runtime, the vote average, the vote count, and the number of recommendations. All of these could be features that are indicative of taste for your movies, so we can create this table and also take a look at it. So from lakehouse.movie features we end up with something like this. Okay, then we are going to create a table movies that combines the movies and their features, and now this table will be a relational table, and we'll also add a primary key, and make sure that we add some vectors now from PG vector. So we have 8 features that we compute. We are going to compute text embeddings of size 768, and then we are going to also concatenate these 2 vectors into a vector that is 768 plus the 8 features, although these features didn't have much of an impact, so we ended up not going with them. We only use vcontent, but I'm going to show you how to do this anyway. Essentially we just create a table where we have the ID, the title, the release year. This is purely works as metadata for us to debug, and then we have the features, and we have the text that we are going to consider for embedding. We are going to essentially concatenate all of these into a single string, and then we are going to apply we are going to compute embeddings for this. So let's go into the pgcli and create this table. This will take a while. And now let's compute the embeddings. So what we are doing here is just computing some kind of an embedding based on the features. So essentially it's just an array with the features. It's not really an actual embedding. An embedding would mean that we are transforming something, and in here we are just using features. It's just a vector of features, really, an array that we then convert into a vector. And there we go. And we can look at what we have so far. We have the ID, the title, the year when it's available, and then we have all of our features and our text, and then finally we have the vector of features over here, only 8 features, and then we'll have the text embeddings over here and the combined vectors over here. Let's go compute that now. So we use PGAI for this, and PGAI is able to create the embeddings table itself. So first we're going to make sure that we have no embeddings table over here, and then let's look at this create vectorizer. The syntax for this has recently been updated for version I believe 0.10, but I'm still using the old syntax, but you can go into this link over here and check it out for the newer versions. So this version of the create vectorizer function takes the table name. So we are going to create vectors for movies. These vectors will be dropped into movie embeddings. This will be a view that combines movies and the movie embeddings store, which contains the actual embeddings. And then we are going to embed using Ollama and this nomic embed text. The number of dimensions, I tried changing this, but the number of dimensions seems to be, for this version at least, to be hard-coded somehow. For each particular model I had to install the newer version to be able to get some feedback on the number of the dimensions it expected to get, and I set it to that number. So for nomic embed text it's 768. For newer versions of PGAI this is probably corrected, and it's going to work slightly different. They are moving away from such a database-centric approach to more of a Python library that creates their own tables on Postgres. Then we are doing chunking over here, where the chunk size is 128 and the overlap is 10. So let's create this embedder. Vectorizer. There we go, we have created the vectorizer, and now this will require Ollama and PGAI worker to be running, and you can check the status by selecting this. Don't forget that you need NVIDIA's toolkit for Docker for it to run properly. So let's look at the job. Is it, so it's apparently it's processing, and as you can see we are currently processing. I've got 8 gigs of GPU memory, so 8 gigs of VRAM here, and it's not using all of the 8 gigs, so the model fits quite comfortably into VRAM, and it will be computing for a while. I've already pre-computed this, it took a few hours to run, so I just created a dump that we can import and use instead of having to to wait for this long. We can check whether the movie embeddings are being computed, so let's take a look before we stop it and restore the dump instead. So as you can see, we've got a ton of embeddings already computed. but this is extremely slow even on the GPU. I also created this query to help me track the progress, and you will be able to check how slow this actually is by looking at this query. So we have only processed, since we started, about 6.5k. We still have 655k, and the progress is at 0.98%. This goes up to 100, so you can see that this will take a few hours to compute. Perfectly doable though, because this is a pre-computation. You could do it as long as you have a graphics card. I'm running a 360 Ti, so yeah, you can do it perfectly fine at home. Again, like I said, this can take a few hours, and you can stop the job by running this query. So we are going to stop it and drop all tables as well, and we can check whether it's running or not. And as you can see, the job is stopping. The GPU 3D engine is no longer active. I've got video decode active, but that's just because I'm currently capturing the desktop and the webcam and rendering this. So we are not just going to restore the embeddings using our restoration script. Let's switch to the terminal and run that. So we're going to leave pgcli and go into the scripts directory, and in here we've got an embeddings restore script that takes the dump file. I believe this C means that we can reset any existing tables. I'm going to try it without the C. So we've got our dumps here, and it's copying the dump into the Postgres Maximalism container. And now it's trying to PG restore from within the container. There we go, we just restored this almost 3 gigs of vectors into Postgres, and this should be under the movie embedding store table. So let's just check to see if that is true. So if we go into moving embedding store, we should have about 662k embeddings. We can look at the data itself just to make sure the embeddings are properly. Let's just do it for the first 10 records, and as you can see, yeah, we have the data restored. Now let's update the movies table on our public schema with the embeddings, because it's still empty and we want to use that table instead of the embeddings table. And after almost 2 minutes we are back, and it has been updated. So if now we go into movies and look at the first 100 records, we can see that we have V features as well as V content. We are only missing the V combined vector. So we can now drop this table for movie embeddings. This will save us some space. and now we can create a v-combined vector that combines the features and embeddings into one. This is the concatenation operator for two vectors. And again, after 1 minute and a half, we are back. Let's take a peek at the end result. Now let's just look at v combined, which is the one that we are interested in. And here we are. We now have the 8 features, and the remaining of the vector is text embedding. So finally, we can create the index that will let us calculate the k-nearest neighbors approximately, and will support the cosine similarity, or rather the distance computations. This takes approximately 30 minutes to create, so I will create it and be right back. And it's 26 minutes later, and the index was just created. We can now go and continue working on our recommendation system. So now we are going to create a trusted movies view based on the vote counts. We are only going to recommend movies that have been voted at least 10 times. And now let's create a user profile, like a fake user profile, as a temporary table. We're going to simulate a user 1, and we're going to create a profile based on movie ID, title, year, and the vector that for the text embedding that we are going to use to recommend based on similarity, on k-nearest neighbors. And we are going to include in this profile the Pope's Exorcist, the Crocodile Dundee movies, except the last one, the third one. We are going to include the Back to the Future trilogy. We're going to include Time Trap from year 2017, and we're going to include Terminator 1 and 2. Okay, and so let's create and look at this table, the profile, and this is the user profile that we are going to take into account. Most of these movies are time travel movies, 80s action flicks, or we've got one outlier which is a horror movie. So based on this profile, we are going to compute some movie recommendations, and this is going to be done based on the average vector across all movies. So this means that we are going to compute the average for each dimension of the vectors of the movies that make up our user profile. And then we are going to use the cosine distance, which is given by this operator. We could use the L2 or Euclidean distance using this operator, or the negative inner product, which is essentially inner product would be a similarity metric, and the negative inner product gives you some kind of a distance metric. And we are going to recommend movies that are not on the user profile, so they have to be new to the user, and order by distance. The closest movies will be on top, and we are going only to retrieve 10k recommendations. Let's do this now. Let's first drop table movie recommendations. if it exists, which it does not. And now let's create the recommendations. And now we have 10k recommendations on this table. We can look at the top 100 recommendations. And here we are. This poll movie is about an alien. Initially I thought it was a bit outside of the taste profile, but it actually feels quite similar to Crocodile Dundee in terms of how it is recorded and scenarios. And then we have a bunch of we have this Vampire's Assistant, and we have a bunch of movies from the same epoch. We've got Bill and Ted's Bogus Journey, which is a time travel movie, Bill and Ted's Excellent Adventure, Time After Time. We've got even Flash Gordon. We've got a few movies that could match the profile, even with a simple, we are just computing the nearest neighbors based on text. But one thing that makes it perhaps more interesting is when we apply a bit of filtering over the recommendations, and we look at vote counts, so least known movies, and make it recent, at least after the 1970s. And so here we have got Time Bomb, Swashbuckler. We've got a bunch of interesting movies that could match this user profile. The user profile itself is quite limited, so there aren't too many movies. Maybe averaging over the vectors is not the best strategy, but this is enough to showcase how we could build a very simple recommender system based only on the text fields that illustrate each movie. Now that we have the recommendations, we are going to use RAG to summarize in natural language what type of movies were recommended. So let's first create textual results based on our movie recommendations. We are using the filtering we applied before, and we are concatenating all this into a text string that illustrates each movie. Okay, so we created this temporary table, and now we are going to send this to Ollama via PGAI. We are going to use DeepSeek with 1.5 billion parameters. We're going to send it the following prompt. Below is a ranked list of movies. Based on the provided information, write a single global summary in a paragraph or two, focusing on the overall genre and topics. And then we are going to send it the movies with a rank, a title, the year it was published, and the genres, and finally the tagline as well. There is one. And then this will give us a nice summary. Let's test it out. We can track the task manager, and as you can see, it is being processed. It doesn't take too long. It should be ready by now. In fact, let's redo this in VS Code, which is probably easier to read. So in VS Code we don't have the temporary table, so we'll have to recreate the temporary table. And we're going to create the answer with Ollama, and here we have an answer which we can open in the editor for easier reading. The list of ranked movies covers a diverse range of genres: action, comedy, thriller, drama, science fiction, family, adventure, etc., highlighting themes such as heroism, moral dilemmas, personal choice, fate, and modern challenges. Notable films like Time Bomb and Swashbuckler showcase action, while others explore themes like The Visitor, The Land Before Time, and Transformers, reflecting various aspects of human behavior and future planning. And so this is kind of a summarization of the results it provided for you. Sometimes when you run this multiple times, you will get better answers. So let's try it once again. So this is using AI Ollama Generate, but it also supports, I think, ChatGPT through the API. And this is a much more interesting answer. So it gives you the genres, it gives you themes that were explored, and yeah, you could add this to accompany your list of 100 recommendations, so that your users know what kind of recommendations were produced. Also with models that are larger, you would probably get a more interesting recommendation, since we are using the 1.5 billion. I think if you go into the Ollama website, let's go there right now. If you search for Ollama models, you can search for DeepSeek R1, which is one that we are using, and as you can see, we are using the one with 1.5 billion parameters. It can go up to 671 billion parameters if you have the ability to load this into VRAM somehow, and probably the answer it returns is much more interesting than this smaller model. And that's it for an example on how to use PGAI to compute recommendations and to compute a simple summarization of the recommended results using LLMs. And I guess this is the perfect time to also introduce WhoDB, which is a part of this Docker Compose that I provide on the GitHub for this video. So let's go into WhoDB. So for now, let's connect to PostgreSQL Maximalism, which is our Docker host. It should be Data Lab Tech, Data Lab Tech, and Data Lab Tech database. Let's see if this works. Okay, and we are connected. Let's go into the public schema. In here you'll see all of our tables that we've been working on, and you'll find the movie recommendations as well. And if you go into the Scratchpad, you'll be able to run a few queries. So let's go to movie recommendations and get the first 10 ones. And here we go. But the interesting feature of WhoDB is this Houdini. Houdini lets you use Ollama, which is installed in here, and we've got DeepSeek, and it lets you ask questions in natural language about the data in your tables. So for instance, how many movie recommendations are there in the movie recommendations table? And yeah, it frequently fails, so it's not really advanced yet, and also this model is not perhaps the best for this. Let's just ask it directly, how many records are there in the movie recommendations table? Okay, and it's got 10k records, and we know this is true because that's what we asked for it to compute. Let's ask it, for instance, what is the most common genre in the movie recommendations table. Okay, apparently the action was executed, but I don't know what the result is. Select genre for movie recommendations. I'm not sure if there is a genre in movie recommendations. Okay, let's just check whether there is a genres on movie recommendations. Yes, there is, but unfortunately it did not output anything useful. But I think this is an interesting idea, and as it gets further along into the development, or if we try to test it with other models, it could be interesting. Now let's look at some pros and cons when comparing Postgres solutions versus an industry standard solution. In this case, we are comparing TimescaleDB with InfluxDB for time series management. So InfluxDB lacks focus regarding the query language. They first launched around 2013 with InfluxSQL, a fairly limited SQL dialect. In 2008 they released Flux, an entirely new language, and I believe they still use Flux mainly. And then in 2020 they began adding basic support for traditional SQL. On the other hand, TimescaleDB was built on top of Postgres, taking advantage of mature features like its query planner for efficient SQL querying. So at the end of the day, if you already are using Postgres, maybe TimescaleDB is a good solution for you. Otherwise, if you don't mind installing a separate solution with a new query language, you could try out InfluxDB. InfluxDB only makes sense if you want to write your queries in Flux, because the SQL it provides is quite limited still. On the other hand, it also conflicts with PG Mooncake, so you might have some troubles there. So regarding PGAI versus Pinecone, which is the original vector store, both pgvector and Pinecone support sparse vectors, but only Pinecone provides a sparse index. Pinecone has no query language, just APIs. Both pgvector and Pinecone support the HNSW and IVF flat indexes, but pgvector scale adds support for streaming this KNN, which was the index that we used on our demo. For most use cases like text embedding, we really rely on dense vectors, so the sparse vectors is not particularly a deal breaker for most AI applications. Maybe sparse vectors are interesting if you are working with graphs, as a graph can be represented by an adjacency matrix, which is frequently sparse. And that's it for another video on Postgres extensions. Next time we'll continue with full text search, graph analytics and message queues. You can find the unedited research notes for this series as a blog post at datalabtechtv.com, and also take a peek at the upcoming final part in this series. If you enjoyed this video and want to support this kind of content, you'll soon be able to donate via Buy Me a Coffee, which will be linked in the channel and video descriptions. Don't forget to drop a like and subscribe for all things data.